occurred?
It's a simple question, but only recently have scientists pondered, what if we had no moon? If we had no sun, there'd be no life on Earth. Indeed, there'd be no Earth. But what of our nearest celestial neighbor, the moon? Without it, there'd still be an Earth of sorts, but devoid of land-based life. Pluto is the only other planet with a relatively large single moon, but these tiny remote bodies are icy planetoids and don't really count. Jupiter, largest of the planets, has 16 moons, but like those of the other gas giants, Saturn, Uranus, and Neptune, these moons are comparative dwarfs. Jupiter and its satellites resemble a mini solar system. Mars has 2 diminutive moons, most likely captured asteroids. In certain ways, Venus is Earth's twin, but the similarities don't stretch to a sidekick. Venus is moonless. So too Mercury, barely bigger than our moon and closest planet to the sun. Within the solar system, only Earth has one big, lucky moon. How come?
You don't want a theory that's so evolutionary that it happens to every single planet, because then Mercury should have a big moon, and Venus should have a big moon, and Mars should have a big moon, and they don't.
If Moon and Earth form together in the embryonic solar system, like Earth, the Moon should have a big iron core. It doesn't, so the theory is suspect. What about the capture theory? Does Earth take hostage a passing planetoid? No dice. A body as big as the Moon just keeps on going. A third theory has the semi-molten proto-Earth spinning so fast that a lump breaks from the equatorial bulge. But the physics don't add up. As NASA prepares to go to the Moon, scientists seek a more plausible explanation.
Harold Urey, the geochemist who was involved in the early planning for the Apollo missions, made some remark that none of the 3 theories work, so the Moon must not be there at all.
But the Moon is there, and from 1969, 6 missions ferry 12 astronauts to the lunar surface.
I was strolling on the moon one day.
But the first Apollo landings are about flags and footprints. Later, though, astronauts look for so-called Genesis rocks, material dating back to the formation of the Moon. Do they solve the riddle of the origin of the Moon? Altogether, Apollo missions return 840 pounds of moon dirt and rock to Earth.
2, 1, 0. This is the other ignition. What a liftoff. And liftoff. Roger ignition.
As soon as the first Apollo expeditions came back from the Moon, there were a series of annual conferences in Houston to look at the rocks that they brought back and talk about the chemistry and the properties of these rocks. People called them the rock festivals. There was one every year.
The results are disappointing. The rocks resemble those in Earth's mantle. They contain no water and little iron. These are no Genesis rocks. And no wonder. Over billions of years, a cosmic bombardment had destroyed the oldest rocks on the lunar surface. To a degree, the hunt for Genesis rocks was a fool's errand. Man walks on the Moon, and the origin theorists are little the wiser.
A number of scientists got together and started thinking, you know, it's been about 10 years since the end of the Apollo expeditions, and we were supposed to be learning about the origin of the Moon and the early history of the Moon. Why don't we have an answer yet?
By concentrating on rock analysis alone, Hartmann believes his colleagues missed the big picture. Impacts, he's convinced, are the clue. The Moon is a stark record of 4.5 billion years of strikes from space. And the Moon's taken some mighty whacks, not immediately obvious from the hemisphere that faces Earth. Prior to Apollo, when the hidden lunar face was barely known, Hartmann had tried to map the craters at the edge of the visible hemisphere. In a lab, he and a colleague set up a special globe.
We projected the very best photographs on that globe and walked around to the side and discovered a whole new class of features that people had missed. Big concentric scars, which are giant, giant craters, 1,000 kilometers across. And that was one of the links in my own thinking, that the moon had suffered large impacts and that there were very large bodies running around the solar system crashing into the planets at the beginning.
And for every impactor on the moon, 25 hit Earth. By 1984, Hartmann is certain. The small iron core, the bone-dry rocks like those in Earth's mantle, the moon has to be formed from the mother of all impacts. That impactor has to be the size of a planet. But can worlds collide? From Russia, a new theory of planetary formation suggests they can and do. Our infant solar system is a maelstrom. From a vast primordial cloud, particles clump together. They grow as big as basketballs, aggregating, colliding. Soon, they're like mountains. The process takes up to 100 million years. We're in the final stages of shaking out the planets. A planetoid blasts the mantle off Mercury. Debris heads for Venus. Beyond is Earth, third rock from the Sun. But next, in the gap before Mars, an extra planet, a rogue stranger called Orpheus. It orbits too close to Earth. On the next approach, cataclysm.
It's a very elegant idea, this idea that occasional big collisions affected the planets, because it allows us to explain why one planet has one type of system, another planet has another type of system. And yet, if you back off far enough and look at the planets in gross detail, they are relatively similar. So you get the similarities, but you get these individual quirky differences.
Venus, for instance, rotates backwards, the result probably of a great smash. Mars has a similar tilt to Earth, a clue maybe of another great impact. The gas giant Uranus rotates on its side, knocked over by a body the size of Earth. Enter a world leader on impacts. Based like Hartmann in Tucson, Arizona, Jay Melosh is skeptical of the Orpheus theory, but he's keen to test it.
As scientists, we are very interested in what happens when two planets collide together. But we'll probably never be able to do experiments with actually colliding planets. And so we have to find some other way of getting the information about what happens during a planetary collision.
Melosh turns to impact specialists, the military.
What we do is the same as the military when they are faced with a problem of determining the effects of above-ground nuclear explosions. We go to a computer code.
Across in New Mexico, a chance word with an insider gains Melosh access to a computer at the Sandia National Laboratories.
This is a classified computer, and so I wasn't allowed to touch the keyboard. My colleague asked me questions about inputs to the problem. And he, for example, asked me, what's the diameter of the target? And I gave him the diameter of the Earth. A few heads came up in the room. Target's the Earth. Then they asked the diameter of the projectile, and I gave them half the Earth's diameter. A few more heads came up around us. And then the velocity of the impact, 11 kilometers per second. Finally, because of the enthusiasm of everybody in the room for this gigantic collision, it was run under highest priority. The results came out. We could see collision of a planet. We could see this massive blast of gas coming out. And it was that kind of simulation that allowed us to go a lot further in understanding what happens in this impact event.
So how is it when worlds collide?
You've all seen movies of colliding planets and things like Star Wars where planets blow up instantly. That's not the way things really work. Planets are so big, things happen slowly. If you stepped back from the Earth 4.5 billion years ago, on that day when the planet Orpheus collided with the Earth, you'd see things happening in apparently slow motion. Orpheus would come in, a body about half the diameter of the Earth, and slowly smash into the Earth, penetrate it, and clouds of vapor would shoot out, but all over about 20 minutes to half an hour. The collision, in fact, would make a lot of vapor that would squirt out. And vapor doesn't obey the same rules as solid rock does. It expands under internal pressure, and that actually allows a fair amount of material to get into orbit around the Earth.
Hartmann gives us the impact. Meloche puts the debris into orbit. But how does that debris form a moon?
It's really sort of a random chance what body collides with what other body to yield the final planets. One of these chance collisions happened to occur at just the right angle with just the right speed to form our moon. And when you view it in that way, the fact that Earth ended up at such a habitable distance from our sun with our large moon seems to be a very fortuitous event.
No such luck for Mars. 2 little satellites, one of them destined to hit the planet. An impact smashes an inner moon of Uranus. It leaves the planet with a set of rings and a reconstituted satellite, the moon we know today as Miranda. Saturn and its rings, billions of particles, as small as sand grains, as big as trucks. The rings are probably the remnants of a moon, one that strayed too close and was torn apart by Saturn's pull. Or perhaps the moon was pulverized by an impact. Either way, the rings are too near Saturn to remake a moon. They're within what astronomers call the Roche radius. Outside the limit, moons can form. Inside, material spirals into the planet, the future fate of Saturn's rings.
The specific type of impact needed to form a moon as large as our moon is actually fairly unique.
Had Orpheus hit head-on, Earth wouldn't have a moon. The angle of impact would throw up a ring of debris, but because it was within the Roche radius, the debris would rain back to Earth.
Yet in other cases, we find that after an impact, perhaps we form 2 moons that are actually stable for tens of thousands of years.
Canup tries every angle in her Orpheus impact models. A third of her simulations yield 2 small moons, but they're unsustainable partnerships. Alas, 2 moons wouldn't last till today.
What a sight that would have been to have 2 moons in the sky, in very close to the Earth.
With 2 moons, the smaller inner moon either falls to Earth, or the moons ultimately collide. But to produce our moon, Canup takes the most oblique approach.
We found that if you made the impact occur at a very off-center angle, so that the impactor almost missed the proto-Earth entirely, that configuration was very good at placing material into orbit. An off-center impact partially destroys the impacting body, which then passes away from the Earth and temporarily recoalesces before coming back in again for a second hit.
A double whammy.
The entire impact process probably took on the order of a couple days, but it would have been a very bad weekend to be on the Earth.
But our prize is the moon. It forms just outside the Roche radius, 14,000 miles from the surface of Earth Mark II. Accumulating ejecta from a hot disk of debris, our moon rapidly coalesces in from just 1 to 100 years.
If we had been on the Earth right as the moon formed, say 100 years after the impact, the moon would have been truly an enormous sight in the night sky. When you viewed the moon right after it formed, it would have appeared 15 times as large in the night sky